Hello, everyone. Welcome back. Today, we want to talk about systems of linear equations and two variables. Our goals will be to understand essentially first what they are and also the possible outcomes of systems of linear equations of two variables. And then we'll basically think about three ways of solving these. One, solving by graphing, solving by what's called the substitution method, and also finally then solving by the elimination method. So first, let's kind of describe what a system of two equations is, or linear equations. So a system, of course, hopefully from algebra you've seen before, a linear equation is one where linear means that all your variables, no matter how many variables you have, they're all to the first power. Okay. And then a system means you have more than one equation. So for example, here below, this is an example of a system of linear system of two equations of two variables. Both equations are linear in the sense that both x and y are both to the first power. And then we have two variables, x and y. And then as a general rule, how many variables you have, you need that these or equations or something to determine what those are. So for two variables, we need two equations, and we have those two equations right here. This is a system of linear equations in two variables. Now, you can also have systems of linear equations in more variables, but right now we're focusing on two. Now, if you remember then a linear equation, if you graph a linear equation like either one of these, your graph is a straight line. So solutions of systems like this are basic points in graphically are points where the lines intersect. In other words, x and y coordinates, x and y points that you are solutions of both at the same time. So a point that we plug into both of them at exactly the same time and makes each one a true statement. That's a solution. And as we'll see, there are basically three kinds of solutions, three general types of solutions, three possible things that can happen when we have two linear equations with two variables. So since solutions are places where the graphs intersect, you can have what's called an independent system where you have one solution. Let's talk about that. So over to the right. So if you have an independent system, then you have one solution. And so if you do a graph then, very simple graph, and if this is your line, you have two lines. Let's say this is line 1. Let's call it y1, and this is maybe your line y2. Then this point right here where the two intersect, this is your solution. The point where you plug in the coordinates like this system, wherever the solution is, you plug the coordinates in, this x and y pair right here, then they would make, if you plug it in, you get a true statement in both cases. That's what it means to be a solution. So that's an independent system. We have only one solution. Now, another example, what else can happen is, in fact, I'm going to do different order. So you can also have no solution. That's what's called an inconsistent system. And that means there is no solution. Okay, so there's no solution to the system. Now, what that means then, if solutions are places where the graphs intersect, then the only way graphs can be able to intersect is if both lines are parallel. So you have parallel lines. And then what that also means is that both equations have the same slope, but different y-intercepts. So both equations have the same slope. So just once again, as a picture of what that look like. If this, for example, is your y1 right here, this line. So you have another line right here, we call it y2, has the same slope. And basically, if they're parallel to each other, they will never intersect. And so then there's no solution. There's no point. There's a solution to both at the same time. And then the third possibility we can have for two equations with two variables is what's called a dependent system. And a dependent system is what that means is both are equations of the same line. What happens is you just don't recognize that yet. So both are equations of the same line. And what that means then, that every point on the line is a solution. So if you graph this system of two equations with two variables, what you get, you graph your line y1, but then you graph your line y2 and find out it's exactly the same line. Okay, so since solutions are points where the lines intersect, every point on the line is a solution because every point on that line is where both fits both lines. So basically, you just have you have the two equations for the same line. You just don't recognize that at first. Okay, so also what this means is that so let's back up and mention one more thing. It's an independent system. Think about the slope-intercept form of a line. They have different slopes, different y-intercepts. An inconsistent system means that both are, think about y equals mx plus b, you have the same slope but different y-intercepts to be an inconsistent or no solution. Then, for a dependent system, think of y equals mx plus b, you have the same slope and the same y-intercepts. So both equations are the same line. Now, sometimes people say that for a dependent system, you have infinite number of solutions, and that's true, but you have to be careful about saying that. It's not really descriptive enough because although you do have every point on this line is a solution, and there are infinite number of solutions on the line, you have to be careful what you mean by that. It doesn't mean any point in space is a solution, only points on the line. Okay, so for two variables and two equations, two linear system, or a system of two linear equations, these are the only three possibilities. Now, if you have more equations with more variables, there are more possibilities, but for a system of two linear equations with two variables, these are all things that can happen. So first, Bruce, we want to talk about solving by graphing. So to solve the system then is to find the solution. We can solve by graphing. And if we solve by graphing, what that means is that, let's look at an example. You graph both lines. And find where they intersect. Okay, so you graph both lines and find where they intersect. So let's look at one example. This one, so we have this system of two equations. 4x plus y is equal to 3. And 12x plus 3y is equal to 1. Okay, now, if you can either graph them as they are, or also put them both in slope-intercept form. And if you remember slope-intercept form, looks like this: y equals mx plus b. Okay, so what that means in both cases, we want to solve each equation for y. Okay, so if we do that, we solve both for y. So let's actually just make a separation here. And I'll write over here 4x plus y is equal to 3. And over here, 12x plus 3y is equal to 1. This one's easy to solve for y. Just subtract 4x on both sides. And then we get y is equal to negative 4x plus 3. On this side, I have to do a little bit more work. So subtract 12x on both sides. That gives us in 3y is equal to negative 12x plus 1. Then divide both sides by 3. But here the y3's cancel out. And over here, let's separate this into two parts. So we have negative 12x over 3. And then we have on the other side 1 over 3. So here I've simply broken this up into two fractions. Then simplify if you can. So 12 over 3 is 4. So this is negative 4x plus 1/3. Okay, now let's go to Desmos and actually graph both of those. Let me write them down first. Okay, Now, Desmos, you can also graph them in the form they're originally in. Let's write it like this. So y is equal to negative 4x plus 3. That's our first line. Then below, let's write y equals also negative 4x plus 1/3. Actually, hang on a second. Maybe I wrote something down wrong. Give me just a moment. Oh, actually, I apologize. I wasn't thinking. Actually, what I've written here is actually two equations that have no solution. So let me actually change that. I apologize for that. Let me make this instead. Let me change something here. So once again, I apologize. I realize I thought the system I picked would have a different solution. So let me change this. Let me make this instead. Let's make this 6. Okay, make that 6. This one should work better. So 12x plus 6, and then it's going to be 6 over 3, which will be 2. Now, it's still not going to be as easy to, let's find that. Let's make this 2. What am I? I apologize. Give me a moment. I'm not thinking what I'm doing. Okay, we'll just leave it as it is. So let's make that 2. Okay, now this one actually have no solution because they're actually both equations of the same line. Or they actually no, they have no solution because you have the same slope in each case, but you have different y-intercepts. Okay, you can kind of see that better right here. So actually they're parallel lines, they have no solution. Now, the nice thing, we can actually change this around. Let's actually make this different. Let's make this have a +1. Okay, now, so basically what we've done is we simply changed that. And what we have then, we solve this by graphing, is the place where they intersect is our solution. Okay, that's our solution, 0.2 and 2.2. All right, so that in this case, that's the only solution. This is an independent system. That's the only solution because that's the only place where they intersect. So then our solution is 0.2 and 2.2. So the solution is 0.2 and 2.2. That's the only solution. That's where they intersect. This is an independent system. Okay. Well, this is, excuse me. So this has no solution. Sorry, this particular system here has no solution because these are parallel lines. But the one I showed you on Desmos has would have one solution. So these are parallel lines. There's no solution because they have the same slope. Okay, but by graphing, if you graph them, you need 2 lines, then anywhere they intersect then is going to will be a solution. Okay, now let's talk about our first method. We're going to solve them by hand, and that is called the substitution method. Okay, so this is one way to solve a system of equations. And let's go ahead and look at an example. In fact, what we'll do is let's take a look at this example right here. So we'll do this example and we'll explain how the method works. So our first equation is 3x plus 2y is equal to 0. And our second equation is 2x minus y is equal to 7. Okay. So once again, we have a system of linear equations. Both are linear. We have two equations with two variables. Now, substitution method says we want to solve either equation for x or y, and that's a choice. You can solve, once again, either one for x or y. Now, try to make it easy on yourself. So it looks like the best choice here, looking at these, is to solve the second equation. I'm going to label these A and B. So the best thing choice looks like to solve equation B for y. If I do that, so the first thing, subtract 2x on both sides. And so we have negative y is equal to negative 2x plus 7. Once again, just subtracted 2x on both sides of the second equation. Then divide through by negative 1. And that basically just changes all my signs. I have y is equal to 2x minus 7. Okay, so I just solved the second equation for y. And what I do with that is I plug this into the other equation. Always plug in the other equation. Never plug it back into the equation you solve for. Plug into equation A and solve. Because the problem we have here right currently is we have a system of two equations with two unknowns. We don't know how to solve that. What we do know how to solve is one equation with one unknown, with one variable. And that's what we're going to get by doing this. So I'm going to take this right here and plug it back in for y right here. Okay, and so if I do that, then I have 3x minus or plus 2y, and y is, we see 2x minus 7 is equal to 0. Okay. Now, distribute this. So we have 3x plus 2 times 2 is 4x. Then 2 times negative 7 is negative 14 is equal to 0. Combine our like terms, 3x and 4x gives us 7x, minus 14 is 0. And then just solve for x. Add 14 to both sides, we get that 7x is equal to 14. Then divide both sides by 7. This works out nicely to x equals 2. Now, right away, we already tell it's going to be an independent system. We'll see why in a moment. But we tell this will actually give us then one solution with one variable, or one solution, an independent solution with one pair of coordinates that will work. Now, once we have this, we can plug this back into either equation. It doesn't matter because it's a solution to both. So I'll pick the second one. This looks like it might be the easiest. So let's say plug this into equation B and solve. So equation B is 2x minus y equals 7. Now the x, so here we have 2x and x is 2 minus y is equal to 7. So of course 2 times 2 is 4 minus y is equal to 7. Subtract 4 from both sides. We have that negative y is equal to 3. And then of course divide by negative 1 or multiply by the sides by negative 1. We get that y is equal to negative 3. Okay. So our solution to the system is 2, negative 3. Now, let's go back to Desmos and make sure that's true. Okay, so let me actually get rid of both of these. But we can also, you don't have to solve for y to graph both. We can actually graph them as they are. And so we have 3x plus 2y is equal to 0. And we have 2x minus y is equal to 7. Okay, and if we check, make sure this is the same thing, right? So that's what we got. Our solution, we have one solution, and they only intersect at one point, and that solution is the point 2, negative 3, which is exactly what we got. Okay, so that is called the substitution method. So you solve one equation. So you pick, this is a choice. You pick one equation, solve it for one variable. And this method works best when it's easy to solve one equation for one variable. In this case, it was. Solve the second one for that. Plug that result back into the other equation. So you get one equation with one variable. Then you solve that equation to get one of your variables. Then plug that. And then you finally get to this point. Then plug that one into either one of the original ones to get your other variable. Okay, so that's called the substitution method. Now, Let's look at the next method, which is called the addition method. Sometimes called the elimination method. This goes by either name, addition or elimination method. I'll let you go here. Let's talk about how it works. Okay, we're actually going to look at the same example. So we'll get exactly the same result, just a different way. 3x plus or minus 2y, I suppose. No, 3x plus 2y, my mistake. So 3x plus 2y. Trying to get it right, is equal to 0. And then 2x minus y is equal to 7. Okay, I'm going to label these A and B. Okay, so let's talk about how this method works and why it works. Let's come back over here to the left. So the addition method, it says, our goal is going to be is we want to add these equations together. Essentially, we're going to add straight down, combining like terms. What we want then is we want to do it in such a way that one variable will go away. One variable will cancel out. Okay, so let's talk about how to do that. So if you recall, two rules for solving any equations, we can multiply or divide both sides of an equation by the same non-zero number. That's a general rule for any equation. Another rule is you can add or subtract the same value to both sides of an equation. Okay, so we're going to use those two rules then to help us out in solving this by what's called the elimination method. So we need to pick a variable to eliminate. And once again, you can eliminate either variable. But it's also best just to make life easy on yourself. So I'm going to eliminate y. At the moment, that's the easiest one to eliminate. Okay. So what I mean by eliminate is I'm going to add these two equations together. It means I'm going to add my y terms, 2y and y. Now, right now, if you add them together, they won't go away. Okay, you get like plus y. But think about what this number here in front of this y needs to be. So when I add my y terms, they go away. And you can tell that's going to be -2. If this was a -2y, if you add 2y and -2y, you get 0y. Because remember, our goal is to get one equation with one variable. So what we need to do then is want to multiply equation B by 2. Okay. Sometimes you may have to multiply one or both equations by something to make this happen. In this case, we just need to multiply this equation by 2. Okay. So if you do that, then we're going to have 2 times equation B. So 2x minus y is equal to 2 times 7. Okay. If we do that, then remember our first equation is still the same. So I'm going to write it again. 3x plus 2y is equal to 0. And now my new second equation, 2 times 2 is 4. That's 4x. Okay. Minus 2y is equal to 2 times 7, which is 14. Okay. Now, what I want to do now then is, now that I've done that, is add these together. Add these equations. That means add straight down, combine like terms. If I do that, 3x plus 4x is 7x. Negative 2y minus 2y is plus 0. There's no more y's. And then finally, 0 plus 14 is 14. Now look what we accomplished here. Is, remember, the problem was having to solve two equations with two variables. Like in the substitution method, we found a way to get down to one equation with one variable. Also, here we're doing the same thing. By adding these equations like this, we now have one equation with one variable. Okay, so we have 7x is equal to 14. And then divide both sides by 7, x is equal to 2. That's what we got before. Okay, and I'll say, so now from this point, we would plug this back in. I'll just go ahead and do that anyway. So now this is the same with both methods. So I'll just say plug in either equation. I'll say plug into equation B to find y. Okay, or you can plug in either equation. So plug it into equation B as we just did before. And so that's going to be 2 times x, which is 2, minus 7. Sorry, minus y is equal to 7. So I get that 4 minus y is equal to 7. Then subtract 4 from both sides. Negative y is equal to 3. And so y is equal to negative 3. Okay, so once again, our solution, the same as it was before, is the 0.2, negative 3. This is the same system. It has to have the same equation, and it does. Okay, so that's the addition method. So you start it with two equations, and you multiply one or both by something. So you basically, when you add one of the variables, that variable will go away, and you end up with one equation with one variable. Okay, let's take a look at another example of that, and also take a look at something else can happen. So far, we've only seen independent systems with one solution. Let's look at something else that can happen. And so let's take a look at this system. So we have 2x plus 4y is equal to 3. And the second equation is 3x plus 6y is equal to 8. Okay, I'm just going to call these A and B. All right, give me a moment to decide something. Right. Okay. So this time, I think I'm going to choose to eliminate. I'm going to eliminate x. That's a choice. Eliminate either variable you want. Okay. Now, this time, you notice it's not like the first. It's not quite as simple. Okay. So this is much like finding a least common denominator. So we want to make this number here in front of the x in both cases something where they're both the same, except one is negative, one is positive. And so it's a lot like finding a least common denominator. We want to find the smallest thing that both 2 and 3 will go into evenly. Okay, and actually that's going to turn out to be 6. So what we'd like then is this to be 6, and maybe this to be either this would be 6 and one be positive, one be negative. Okay, and that's also a choice which one want to be negative. What I'm going to do to make that happen is I'm going to multiply equation A by 3, and then I'm going to multiply equation B by negative 2. And once again, which one is negative is up to you. So if I do that, multiply the first equation by 3, so 3 times 2x plus 4y is equal to 3 times 3. And the second equation, negative 2 times 3x plus 6y is equal to negative 3 times 8. Okay, so now let's look at both equations. And so 3 times this is going to give me 6x plus 12y is equal to 9. Then multiply the negative 2 by the second equation. Negative 6x minus 12y is equal to negative 24. Okay, look at that. Make sure you agree with that. Now, my next step then, once I do that, and once these are matching, except one's positive, one's negative, I'm going to add those together. Add straight down, combine your like terms. Now, this does eliminate the x, which is good. What happens in this case, it also eliminates the y. So actually, this becomes 0. And over here, we have 9 and 24. Negative 24 is going to be positive 15. So we have a 0 equals 15. Okay. You notice what we did is we chose to eliminate the x, which we did, but ended up eliminating the y as well. So we have 0 is equal to 15. What's important here is this is a false statement. And it's always false. I've eliminated my variables. There's no value of x and y I can ever plug in that'll make this a true statement. So what this tells you when this happens, and if this certainly happens either with the substitution method or the elimination method, either one, this can happen with the substitution method, true, we get a false statement with no more variables. And what that tells you then is there is no solution. These are parallel lines. Now let me just circle that, okay? There's no solution. So let's actually take a look. Let's graph both those on Desmos and see that that's true. Okay, so let me just blank these out for a moment. Okay, so what I had was 2x plus 3y 4y is equal to 3. And my second equation was 3x plus 6y is equal to 8. As you can see, those are parallel lines. So if you actually solve them both for y, put them both in slope-intercept form, you see they have the same slope. Okay, so since a solution is a point where the lines intersect, these lines never will intersect, and so there is no solution. Okay, so that's what happens with either method, substitution or elimination method. We get a false statement like this. It could be 0 equals 15, or it could be like 7 equals 15, something like that. With no variables, that means you have no solution. Okay, let's take a look at one more example. Once again, I will use the elimination method again. Or I might go back to the substitution method, do one more example of that. Yeah, let's actually do that. So this time our system is going to be 2x plus y is equal to 4. And the second equation is 4x plus 2y is equal to 8. This is my A and this is my B. And this time I'll actually use the substitution method again. All right, so this is also going to do that for, because we can easily solve the first equation for y. So let's do that. I'm going to say solve equation A for y. Okay, and all I have to do to solve that for y is to subtract 2x on both sides. And so that will give me then y is equal to negative 2x plus 4. Now, remember, once I do with that, is I plug this in for y, just replace y here in the second equation with this. Always plug it back into the other equation. So I'll just say plug into equation B and solve. If I do that, I have 4x plus 2y, and y is this, negative 2x plus 4 is equal to 8. Once again, so distribute. So I'm going to have 4x, then this is going to be 2 times negative 2x is minus 4x, and then 2 times 4 is plus 8 is equal to 8. Now, if you notice, these cancel out, so I'm left with 8 is equal to 8, or if you subtract 8 from both sides, that's also 0 equals 0, however you want to think of it. Other than this, either here or here, this is a true statement. Of course, 8 is equal to 8, or 0 is equal to 0. Now, if you get a true statement, what this means, you have a dependent system. Okay, remember what dependent meant? They're both equations of the same line. And we'll look at that in just a minute. Both are equations of the same line. Okay, now the way we're going to write our solution is we're going to use a kind of an unrelated variable we're going to call k. What I'm going to do then is I'm going to write it as a collection of points k, and I'm going to pick one of the equations. I'll just use this right here. Negative 2x minus 4. I'm right, that is negative 2k plus 4 rather. Okay. Now let's explain what the solution means. Okay. So what happens is either both equations of the same line. So any point on this line, so if I solve the second equation for y, I would also get this. So any point on this line is going to be a solution, both, because they're both equations of the same line. So what I'm doing right here, instead of using x or y, I'm using kind of dummy variable k. I'm saying pick any k you want, and that for your x, and then this will be your y right here. And this y was found by solving this for y. This is the equation of our line. So give me any k you want, and you plug that in. That will be my y coordinate. And this point then you get will be a solution on that line. So let's go back to Desmos and take a look at both of these. Our first equation was 2x plus y is equal to 4. And as we'll see, I'm going to type this in. We get this, it's just going to be the same line, maybe with a different color. So 4x plus 2y is equal to 8. Okay, yeah. So you can see if I turn this one on and off, toggle on and off, they're both equations of the same line. Actually, if you see that, if you divided this equation by 2, you would get this equation. Okay, so our dependence, so every point that's along this line is going to be a solution. And that's what the solution we found. You pick any k you want, and then you make your y negative 2x plus 4. You'll get some point on this line, and then that then will be a solution. So pick any k you want, make that your y, plug that in and find your y. That point will be on that line, and then will be a solution. Okay, so let's review what we've seen so far today. So we've seen that when you have linear equations, two linear equations with two variables, remember linear meaning that all your variables are the first power. You have three possible types of solutions. You can have an independent system with one solution. What's called an inconsistent system with no solution. They're parallel lines. Then a dependent system where both are equations of the same line. Then we looked at three different ways of solving. Solve by graphing. So graph both lines, find out where they intersect, if they do intersect. Then we had two other methods, a substitution method, where you solve one equation for one variable and plug it in the other one, and then get your solution that way. And then the addition method, where you multiply one or both equations by something, so when you add them together, one variable goes away. Then also we saw that in this case, a case like this, either with either method, if you get a false statement where you have no variables left on a false statement, such as this, 0 equals 15, which is always a false statement, that means there's no solution. Then, if you get something like this, where you get something that's always true, either 8 equals 8 or 0 equals 0, something's always true, that means you have a dependent system. They're both equations of the same line, and you write your solution like this, where you write it as k or some dummy variable like k, solve one equation for y, and then make that result you got for y is your y coordinate. In the future, we'll look at how to solve systems of more than two equations with more than two variables. And that we use often different methods of matrices. Thank you. Have a good day.